Good. So what we've done so far is looking at planning is we looked in terms of this strips representation that's defined in terms of the preconditions, what has to occur before an agent can do an action, and the effects of how does the action change the world. And you have a strips assumption, which is that the features not mentioned in the effects are not affected by the action. So it's trying to have this locality of representations of action so that we don't have to write down a function we don't have to sort of represent explicitly as a table from states to actions into new states. And then we had this forward plan where the nodes are states and the arcs are actions. So we started off with just this initial state. Okay, are there any questions about that? Okay. So this is the example. And let's start off with some clicker questions. The best way to learn this is just to try a few examples. So let's try a few examples and see how we're going. PUM is the actions pick up mail. And given this thing, what would you expect the preconditions to be? The robot location is MR, which is the mail room. Mail waiting is true. The robot has coffee is false. Sam wants coffee is false. The robot has mail is false. The location is the office. Robot has mail is true. And E, robot has mail is true and mail waiting is false. So what do you expect the precondition of pick up mail to be? Does anyone need more time? Anyone need more time? Good. Yay! All right, good. Right. Pick up mail has to be in the mail room and mail waiting has to be true, otherwise it can't pick up the mail. All right. It's the same alternatives, but now it's the effects of pick up mail we're interested in. So what do you expect the effects of pick up mail to be? All right, does anyone need more time? Okay, 3, 2, 1. E. All right, good. It's not so hard after all, is it? No, good. All right, one more just to make sure we're all on the same page. Oh, sorry. Deliver mail. What are the preconditions for delivering mail? Oh, hang on, what's the answer to this? Does anyone need more time? Right, it can deliver mail when it's in the office and it has mail is true. So that's when we can deliver mail here. Okay, does that make sense? Right, it can only deliver mail to the office according to this funny thing we had before. Yes? The question is, after it's picked up mail, is... Will mail waiting be false until it's mail waiting will be false. After it's picked up mail, mail waiting becomes false. No, but I mean, does it stay false until the mail has been delivered, or does it become true? Well, no, here we only have actions. We don't have exogenous actions that occur outside. But it could be the case that it starts off holding the male and there's still male waiting. So we don't exclude that. Okay, does that make sense? Pretty soon we're going to get to the case about where we have outside actions that actually affect the world, but right now we don't. Now we have a very simplified domain. Okay, any other questions? No. Why doesn't let me do that? D. And what's the effect of deliver male? Okay, does anyone need more time? Stop. All right, wherever it has male is false. Good. All right, now, that was just about the representations, and I just wanted you to make sure we all knew what these were. And now what we're going to do is we're going to have this is about the forward planner. So given this state where the robot location is it's in the office, it has coffee, Sam wants coffee, there's no male waiting, but the robot has mail. And I want to know what the resulting state after delivering the mail is. And you just told us what the effect of delivering mail is, so there shouldn't be, so there's no surprise here. Everyone knows what the result of delivering mail is. So what's the resulting state after delivering mail? How are we going? Do people need more time? Does anyone still need more time? Okay. So the only thing that deliver mail does is it just if robot has mail, it makes it false. So it should be exactly the same as before, except robot has mail is false. And so that one is C. Right, does that make sense? You just told us before what Liston did. All right. Now it's the same alternatives, but the only difference in this is the action is pick up mail. So the only difference between this slide and the previous slide is that the action is pick up mail. So the question is the resulting state after picking up mail. It's the same state it was before. And they're all the same alternatives. Oops. All right. Does anyone need more time? 3, 2, 1. Right. The answer is E. You can't do it because the precondition for delivery, pick up mail, which everyone just did, was that the location had to be in the mail room and the location is in the office. Okay, does that make sense? D is no effect as well. Hmm? Nothing changed in D, so D is also no effect. Well, but there isn't a resulting state. See, but the point is in this thing, we only have arcs corresponding to actions where the preconditions hold. So it's not as though we have this arc that doesn't exist where the precondition does. The only thing that exists in this forward planner is the arcs where the actions exist. Okay, does that make sense? So everyone can do a forward planner now. It's just repeating this over and over into search space, okay? Any questions about how this forward planner works? Good. So what we're going to do today is we're going to finish off talking about a few remaining issues with this forward planner, and then we're going to talk about something called a regression planner, which instead of starting from the initial state and searches forwards, it's going to start from the goal and search backwards. And then we're going to talk about how to represent planning in terms of a constraint satisfaction problem. Now, a few things to note about the forward planner is that the search graph can be constructed on demand. So the idea is that we're only going to construct these reachable states. So you shouldn't think in here of terms this search graph exists before we've done it, before we do it. All we're doing is we start with a node, and we're going to construct the graph on demand. So it's not as though we have this state space at all. Most state spaces are far too big to do this. So that's the first thing just to notice. And the second one is if we wanted to cycle check or a multiple path, we need to be able to find repeated states. And that depends on how we represent the states. And there are a few ways of representing the states. One is a specification of a value to every feature. And it turns out this is actually very expensive to represent the value for every feature, because you have to, every time you do an action, you have to recopy this whole data structure, and it becomes very expensive to represent that. If you have enough features, this becomes unmanageable. And what you often do is just to represent this as a path from the start state. So you can just know the path, and then you can work out, because it's very easy to work out what's true in a path, because it's just the adds and deletes. So you can work out what's true in any node just from following the path. Okay, so then there's all sorts of different ways of representing it, but the typical way to do it is you just represent the path from the start state. Right, you might have this start state, and you might move clockwise to a new state, pick up mail. And it's pretty easy from this state, just knowing these actions, to know what's true here, right? It has, if this was the location, it must have mail is true. It must be in the office, and everything else that's true here is also true. Okay, so given this path, it's easy to compute what's going on. But then it makes it slightly more difficult to find loops, because you have to work out what gets added and subtracted. That's sort of an... Okay, so it's not obvious you want to store these things, although they're claimed to be just like dictionaries, it's not obvious you want to store them as dictionaries. It's much better just to compute them on demand and save space. Okay, does it make sense? Okay. So what we can do is we can then use domain-specific knowledge in terms of a heuristic function that estimates the cost to a goal, just like we did in searching. So that's typically what happens in these ones, as people have invented sophisticated heuristics to solve these. So sort of the state of the art in planning is often a forward planner with sophisticated heuristics to work out how you're estimating the cost. So that should be obvious, and playing with some of these is part of the next assignment. So think about how you could actually do some heuristics. But you've already done heuristics, so you should know how to do that. And the other one is to do sort of domain-specific pruning of neighbours. So for example, one of the things might be, well, don't go to the coffee shop unless, well, why mightn't you go? When would you not want to go to the coffee shop? When do you want to go to the coffee shop? Yeah. Right, so one of the things you could do is to say, don't go to the coffee shop unless Sam wants coffee, is part of the goal, right? And you don't already have coffee. So you might tell it these very specific constraints about when not to do things. And don't pick up coffee unless right? Unless, when would you not? So you don't pick up coffee, you don't even try to pick up coffee, it's just not going to be part of it unless, right? Unless Sam wants coffee, right? So they're pretty dumb things, but the forward planner doesn't know these things, right? You might tell it these things that are sort of pretty obvious to it, and we can put in a whole lot of constraints about pruning this search space before we start. So people put in domain-specific knowledge in here. And another one is don't go clockwise if the last move was to go anti-clockwise, counterclockwise, unless it's reasonable to waste time. So never go forward and backwards unless wasting time is what you want to do, which it might be. So there's a whole lot of domain-specific knowledge that you could do in here. So when people build these systems, they typically put in as much this domain-specific constraints and the heuristic function, because otherwise the goal doesn't affect your actions. Okay, because in the forward plan, the goal doesn't affect the actions unless we have a heuristic function. We can also put in these domain-specific pruning things. Okay, any questions about that? All right. So what we're going to do for the rest of today is talk about something called a regression planner. And what we're going to do is search backwards from the goal description. And the nodes are going to correspond to sub-goals, and arcs are going to correspond to actions. So the nodes here are propositions, an assignment of values to some of the features that should be achieved, and we're going to call them sub-goals. So in here we're going to just think of this as a node, where this is not an assignment to all the variables, just an assignment to some of these variables that have to be achieved. And it'll make more sense when I give an example in a second. So just nodes are assignments of values to some of the variables that we're trying to achieve. And arcs are going to correspond to actions. And the neighbors of this particular node are going to achieve at least one of the variables that need to be assigned. So it's essentially we're thinking about what the last action is that's going to achieve this goal. And the neighbors of some node associated with an arc specify what must be true immediately before the action, so that n is true immediately after. So we're going backwards. We want to know what must be true before the action in order to do it afterwards. The start node is the goal to be achieved, and so we're going to start with the initial goal we're going to try and achieve, and then goal of n is true if n is a proposition that's true of the initial state. So we're now searching. We want this one when we can stop searching. We can stop searching when we've reached something that's true of the initial state. So let's have an example of this. So this is an example. So the goal here is we want Sam to not want coffee. Right? The goal is Sam want coffee is false. And what we're going to do is we're going to try and find an action that will achieve Sam wanting coffee is false. And if you think about all these actions, the only one possible last action is to deliver coffee. Right? So we're going to put it this way. So DC is the last action, is going to be the last action in the plan. The last action in the plan. And there's only one last action in the plan. The only thing that, because this is going, once this is achieved, we're going to stop. The only thing that can make this achieve it is deliver coffee. Right? Does that make sense? So deliver coffee is the only possible last action in the plan. It's the only thing that achieves one of these things. So then what must be true immediately before deliver coffee? Well, if you think about the deliver coffee, what are the preconditions for deliver coffee? Well, it has to be in the office, and the robot has to have coffee, right? So we're going to write this as robot location is the office, and robot has coffee is true. These must be true immediately before deliver coffee so that Sam wants coffee is true. So these must be true immediately before before deliver coffee. Right, this is actually just the preconditions of deliver coffee. And you all know what the preconditions of deliver coffee is because you just did that. Does that make sense? So if we ever got to this state here, and then we delivered coffee, then Sam would want coffee is false. So now we're going to try to achieve these two things. Now what we could imagine a plan that says, well, let's achieve this one, then that one, or that one, then this one, but actually it turns out that doesn't work, and maybe we'll give an example next time of this. But what we'd like to do is we'd like to find out what actions can achieve one of these things. And we could achieve robot location has car office. And the only two actions that can achieve this is to move clockwise or move counterclockwise. And what could achieve robot has coffee? What could achieve this? No, we actually want an action that would achieve this. What has this on the add list? Pick up coffee, right? So let's look at this node here. Okay, they're the only things. The only things that achieve robot location as office is to move clockwise from somewhere. I know where it is. Move counterclockwise from somewhere, or it can achieve robot has coffee. What about this node here? What about down here? What has to be true here? Yeah, the location has to be the coffee shop. But if the location is the coffee shop and you pick up coffee, is this true? No, right? So if this was true in order to achieve this, then it wouldn't be the case that this whole goal is true. Right? So this cannot exist, doesn't exist. It's impossible for this to be the thing because it needs to be in the location, it needs to be in the coffee shop to achieve this, but also needs to be in the office to achieve this. Equals office. And that can't exist. And that's why it doesn't exist on this map. And now we have these two. So these are the only two second to last actions we could do. Right? They're the only two second to last actions that are sensible to do. And so where would we have to be in order to move clockwise to, we're going to move clockwise, and now the robot location's the office. Let's look at this map here. Where did you have to be? So where do you have to be? I can't see it. Coffee shop, thank you. So our lock equals coffee shop. And what else must be true? Right, you also have to have robot has coffee as true. Because the only way for both of these to be true after you move to coffee is for this to be true before you do it. Okay? And you could also move counterclockwise, and I just messed my thing up and have a dog. Whoops. Does it make sense what we're doing? Now we could move, but you could also move counterclockwise from where would you have to be to do that? Which way is counterclockwise? I can't see it. Anyone tell me what you have to be true to do this? Right, so the robot location has to be the lab. And what else has to be true? Right, RHC has to be true. So if I'm in the lab, then I move counterclockwise, I'm in the office. Is that right? That's what it's doing. So if I'm in the lab with coffee is true, then I move counterclockwise and these two have got to be true. Okay, does that make sense? So let's pick one of these. Which one should we pick? Well, it's just a search space. We're going to search dumbly. Right, so now we're going to pick one. Let's pick this one. So what actions could it be achieved? What actions could achieve this location as CS? How could we achieve this? We want to achieve one of these things, right? We want to achieve this or this. How can we achieve location as CS? Right, so you can either move clockwise, move counterclockwise to achieve this, or I could achieve this by, or I could do pick up coffee. Does that make sense? So these are the things. I can achieve this or I can achieve this. Now I want to achieve, if I go, so let's do the one that I really want to do is this one. I want to achieve robot has coffee is true. What has to be true before I do this? So what has to be true in order to achieve this? It has to be the robot location is the coffee shop. And if the robot location is the coffee shop and I pick up coffee, then both of these two are true. So now it knows, just by doing this, that it has to get to the coffee shop, has to pick up coffee, has to move clockwise, and then deliver coffee. Okay? So it's going backwards from this goal to try to work out what to do. Does that make sense? Yes? Yeah, we only stop when we get to the, if it's already at the coffee, if it's at the coffee shop, then you can stop because it knows what to do. Right, let's do, let's suppose the robot is, pick a place. Let's suppose it's at the office. Well, that's interesting because if it was at the office here, it had to go back, right? Right, so the fact here, it knows that it acts a circle. So if the current location, if the initial state is the robot location is the office, and robot has coffee is false, then we're going to keep searching here. We're going to keep searching. We have to achieve this. How do we achieve this? What are the actions that are available? Well, we can move clockwise or we can move counterclockwise. So the only two actions that achieve this. There's no point in trying any of the other actions. None of the other actions achieve this. And one, am I moving clockwise? Where does it have to start? Where does it have to be? Is this true? What's this node here? Right, so the robot location equals mail room. Or here, what's this one? You move counterclockwise. Which is counterclockwise. It's going to move. Oh, I can't see it. It hurts my neck too much. What? Right, the robot location is the office. And if you keep following this, we can stop here. So we could stop here. We can stop. We have a success. We tick. We could also go down here and tick as well, because there's another way to do it. You go all the way around the other way. Right, we could go from the office to the lab to the mail room. Right, by keeping, otherwise we could get a cycle in here. Okay, so we could tick here, but there's also a path down here. There's a path down here as well. We do the other path. Okay, so we now know we're here. We need to move counterclockwise. You want to pick up coffee. So you're going to move, it's going to move counterclockwise, it's going to pick up coffee, it's then going to move clockwise and deliver the coffee. So the search space here is much smaller than the other one because it's only doing those actions which it's deemed necessary to do. Okay, any questions about that? Okay, good. So here's the formalization of just what we did. So node n, we're representing this assignment of values to variables. And these are the set of assignments you want to hold. They're the sort of sub-goals. The last action is one that achieves one of the VI. So it's one of the ones that are on the effect list. So x I equals VI is on the effect list. And it doesn't undo one of the other ones. Right? So pick up coffee here. We can't have an action that undoes, that has the effect of it is to undo one of the other ones. We can't have, if we want robot has coffee is here, we can't do an action here that undoes robot has coffee. And then the neighbors along it must achieve the preconditions of the action. The precondition of this was robot is the coffee shop. And it also must achieve all the elements of n that were not achieved by A. So here and here, this action here, moved clockwise, didn't achieve this, and this wasn't on the effects, it had to be true beforehand. And the neighbors must be consistent. We ruled this one here out because it wasn't consistent, because it couldn't be on two different locations. Okay, any questions? Does that make sense? Everyone's happy? Happy, good, all right. So now everyone knows what we're doing, and everyone knows how the algorithm works. Let's try and work out what's wrong with this. One is our goal. We want the goal is Sam to not want coffee. We want the robot to have coffee. And we want there to be no male waiting. So what's wrong with this? So sit there, talk amongst yourselves, work out what's wrong with it. There's at least 5 errors that I know of. 1, 2, 3, 4, 5. At least 5 errors in this. All right, so what are the errors here? Tell me some errors, things wrong. So what do you mean pick up mail is wrong? Where? And what should it be? Right, so 2, the location should be the mail room. Right? Because the only way to pick up mail is to be in the mail room. Okay, and what else is wrong? No, it has to be waiting. Right, so mail has to be waiting. Mail waiting has to be true. Right, the only way to pick up mail is to be in the mail room and to have mail waiting. And then, if those are true and you want Sam to not want coffee and you want the robot to have coffee, they have to be true before you pick up the mail. Before you pick up the mail. Right? So the 2 should be Sam doesn't want coffee. So it should be Sam does not want coffee. Robot has coffee. I want the mail room and I want mail waiting. That should be 2. So it should be, let's write as a set. 2 should be this. Is that right? Because this one has to be true. These 2 both need to be true after pick up mail. Because we want it in the goal. It's in 1. It's our goal. So we want Sam to not want coffee. And so if we want Sam to not want coffee, if we want Sam to not want coffee, after it has to be true before, because it's not going to be achieved by this goal. For 1 to be true. All right, what else is wrong with this? So what's wrong with that? So what's wrong with deliver coffee? What about? So what should happen? So the statement here is that there's something wrong with deliver coffee. And you said it's... So what should this look like? So 3 should be what? No, the goal is correct. The goal is correct. The goal is what we're given. I just numbered the nodes because so I can refer to them. Right. So 3 should not exist. Not exist. So deliver coffee is not an option. Why isn't it an option? Right. Because you can't deliver coffee and robot has coffee is true. So after DC, robot has coffee cannot be true. that make sense? Any questions about that? What else is wrong with this? Yes? Right, so 8, even if 2 were right, you can't pick up coffee and immediately be in the office. 8 is wrong. You can't pick up coffee and immediately be in the office, which is what it says. And in fact, so what should 8 be? So what should 8 be? How should we change 8? How should 8 be changed? So what should 8 look like? Right, so it shouldn't exist. 8 should not exist. So it shouldn't. So 8 shouldn't exist. Let's say it should not exist. In this diagram. So 8 should not exist in this diagram. What else is wrong? Hmm? 7. What about 7? So I picked up coffee when moving clockwise, right. So 7. So 7 should have, how should it be different? So it should have robot has coffee, right? Should have robot has coffee is true, which is star HC. Any more? All right, questions about this? So it's clear what's going on. We'll ask clicker questions next time. Okay. So a few things we could do in here is we can do loop detection, partial path multiple path pruning in sort of interesting ways, because now we don't just have identical sub-goals, but if we're trying to solve a more complicated sub-goal than the previous one, then we can prune it. So goal G1 is simpler than goal G2 if G1 is a subset of G2. So it's easy to solve go to being in the coffee shop than being in the coffee shop and the robot having coffee. Right, so it's easier to solve just getting to the coffee shop than the two of them. So if we have a sub-goal of coffee shop, that is, so if along our path to the node we just have coffee shop, and now we have a node that says the robot has coffee and the coffee shop, we can prune it. Even though they're not identical sub-goals, we can prune it because one's a subset of another. So if you have a path to a node N, you've already found a path to a simpler goal, then you can prune that path. You can prune the path. So it doesn't have to be identical. It's not a loop like we saw before. It doesn't have to be loop. We can actually do more pruning than we could just in the general loop detection and multiple path pruning. Okay. And I think, Then what we can do is we can define heuristic functions. Now we're trying to find how the heuristic function is now an estimate of how easy it is to solve that goal. Not an estimate of getting to the goal, but it's how easy it is to solve the goal from our initial state. So when we start defining heuristic functions, the heuristic function estimates how difficult it is to solve the sub-goal of the current node, the sub-goal that the current node represents from the initial state. So that the current sub-goal is how hard it is to solve that from the initial state. So that's what the heuristic function is. Right? So it's how hard it is to get from the initial state. And we can also, the same way, we could use domain-specific knowledge to remove impossible goals. For example, it could be the case that you know you can't hold two things at once, is often the case. And you can't, it's not obvious from some action description, you can only hold one action off at a time. And if we get to a goal here that's impossible, we want to use domain-specific knowledge to prune it. Of knowing some things are impossible is some sort of domain-specific knowledge that we might use. Okay. Any questions about this? Good. All right, let's stop there. Thank you.